Before start this video, please subscribe my channel and click on bell icon. Thanks.
Bengaluru, Raman Research Institute, RRI, in Bengaluru on Thursday said a group of its scientists have indigenously built an experimental facility to simultaneously cool and trap a large number of sodium and potassium atoms near absolute zero temperatures using laser light and magnetic fields. With the new lab, Quantum Mixtures Laboratory, QuMix, RRI said it has joined a handful of laboratories globally to demonstrate such efficient simultaneous production of a mixture of two species of ultra-cold neutral atoms with interspecies interactions control. Researchers said that results from this experiment can deepen the knowledge required for developing quantum technologies such as quantum computing, quantum sensing, and metrology, all of which are the frontier areas of research. Built over a period of 5 years, this specialized experimental facility comprises 4 interconnected ultra-high vacuum chambers, where atoms are trapped and cooled under a pressure to the tune of 10 to 11 millibar, equal to 14 orders lower than the normal atmospheric pressure. There are multiple intricate laser systems, optical arrangements, and high-resolution detection systems, RRI said. Using techniques of flashing light onto the atoms, researchers said it was possible to manipulate properties of atoms and use it for taking various measurements that are fundamentally quantum mechanical in nature. Using a combination of light and magnetic field, we attempted to cool and trap a large number of sodium and potassium atoms from their mixture at near absolute zero temperature, in microkelvin. As the behavior of atoms is different at such low temperatures in comparison to at room temperatures, we wanted to understand their quantum correlations, Saptarishi Chowdhury from QuMix, who led the latest experimental research, said. Pointing out that in the absolute ground state, dipolar molecules of sodium and potassium possess high dipole moments, offering high versatility to study the many-body physics, perform tests for quantum simulation, sensing and entanglement. Researchers said the advantage of the experiment setup was we can swiftly change many parameters without the need to produce newer samples, as is the case in most condensed matter system experiments, Sanjukta Roy, co-author of the study, said. The study was published in the journal AIP Advances, where it has bagged the distinction of being editor's pick article. Being natural qubits, both sodium and potassium can be subjected to manipulation using tailored light. These then can be excited to any desired state as required for the experiment. The sodium-potassium mixture was used primarily because they offer a perfect combination of fermionic, heavy in weight, and bosonic, light in weight, properties for studies under light. Resonant light was flashed to achieve the quantum state control of atoms, Gaurav Pal, a PhD student, who co-authored the article, said. According to Sagar Sutradhar, a final-year PhD student and article's lead author, the experiment setup includes another trap at the pre-cooling stage known as a cold atomic beam. It is based on the idea of two-dimensional magneto-optical trapping of atoms. This vital intervention was introduced to first cool the atoms and later push them into the main experimental setup, Sutradhar, who designed, implemented and characterized the performance of the system, said. As a result, researchers succeeded in trapping a 1,000 times greater number of atoms compared to the traditional atom traps used in various laboratories worldwide. To be precise, the special experimental setup typically manages to trap 10 billion potassium atoms and about 50 million sodium atoms in the mixture, RRI said. Anirban Mishra, another co-author of the paper, said the simultaneous production of high-power narrow line-width laser light and frequency, intensity, polarization and phase control of these trapping lights is one of most complex yet necessary steps required for successfully cooling such large number. Sayari Majumdar, who also contributed to this work, noted, these ultra-cold atoms, especially in the form of a mixture, are ideal candidates for quantum sensing of tiny magnetic fields. The interspecies interaction as reported in the paper is now being utilized to develop better sensitivity quantum magnetometers in the laboratory. On the observed behavior near absolute zero temperatures, Chowdhury said, as the atoms are inherently quantum mechanical in nature, they do not cool. Instead, they move at rates of a few millimeters/second, and this helps us to study light-assisted interactions between the atoms. Thanks for watching. Please subscribe my channel for more videos.